And then I'm going to release this poll, I think. So it says launch polling, and it simply asks, do you wish to have a review session on Thursday, July 2nd? So if you say yes, we will meet. If you say no, then we will not meet. And I don't know what happens. So I guess you have to answer. Does it show up on your guys' screen?
Yeah.
Mine shows up right
Yeah.
now.
Okay, so you just say yes or no, click on it. Of course, there's only 3 of you. Okay, only 1 of you has responded. 2 of you have responded, and 1. So at this point, we're stuck waiting on, I don't know whether we wait for Matt or not. It looks like, yes, we are going to go ahead and meet. So you don't have to. So if you were the dissenting vote of no, all we're going to do is talk about the R2, no, it's R3 review to date. So we will kind of go over questions that are similar to it, maybe work 1 or 2 that are actually on it. So we will go ahead and meet on Thursday then. So thank you for that. And it works. Woohoo. Now I know for the fall. So it will probably be a shorter session, but we'll go ahead and meet. Get your money's worth. Okay, so today, before I go down through in today, on Wednesday, by tomorrow, section 5.2 and 5.3 are due in MyLab Math. By Saturday, you have section 5.4. It is just 1 section, but you also have the review to date. It's R3. It is available now in the module 3 on Blackboard. You can download it and start working on it. On Sunday, you have your quiz 6 that's due in MyLab Math, and then you also have that next discussion question. I'd like to get a little more activity going on those discussion questions. I realize it's only 40 points out of the grand total of like 1,000 points, but it does show whether or not you're committed to the class. So, and then you can go ahead, ProctorU is now active on exam 3, so at any point in time, you can go get your schedule set for that exam 3 for next week. So, and I think that's our summary. Does anybody have any questions over anything we've been talking about? We're good to go then. Okay. So today we're going to actually graph those rational functions. Again, this is all without your calculator. So you don't want to pull out that calculator to graph it. You're supposed to be able to do it without it. We laid the foundations yesterday, and today we're going to kind of tie yesterday's lecture in with today's lecture and actually graph them. So the first one I want to graph, and that's all the directions are really going to say, is R of X is equal to 2x plus 4 over x minus 1. So 2x plus 4 over x minus 1. And again, it's a rational function because we see x in the denominator, and that's what calls it a rational function for us. Okay, so we've got some very detailed steps to use. The first step we're going to do is we're going to go find the x-intercept. So step 1, find the x-intercept. And does anybody remember from yesterday how we find that x-intercept? We talked about it yesterday. Okay, that's a no. So again, what you're going to do is set the top to 0. So you set the numerator equal to 0 and solve it. So that's 2x plus 4 equals 0. When you solve that, you'll get 2x equals a negative 4, and you'll get x equals a negative 2. So our x-intercept, and I'm going to have issues here. So I'm going to, this is the one place where I need the huge boards that are in the classroom, is just to record all the information because there's no way I'll get it in. So I'm just going to start logging the stuff as we find it over here. So the x-intercept is at negative 2, 0. Okay, and because I like to do all the intercepts first, our second step is going to be to find the y-intercept. That we know how to do. We're just going to plug in 0 for all the x's. And if you plug in 0 for all the x's, in the numerator, you're going to get a 4. In the denominator, you're going to get a negative 1, which gives me a y-intercept of negative 4. Let's make sure step 1 does make sense to everybody. So again, the reason you only need to set the numerator to 0 is because if you set the entire function to 0, you'd clear the denominator as the first step, which would get rid of the denominator, and you still have the numerator equal to 0. So, okay, step 3 is the vertical asymptote. So we need to find the vertical asymptote. And that comes from the denominator. We talked about this yesterday. You're going to set the denominator equal to 0. and solve it. So for us, that's x minus 1 equals 0 or x equals 1. Now this is a line, so I'm going to write it as a line. It's not a point. It's just the line x equal to 1. So over here, vertical asymptote, x equals 1. And again, an asymptote, a vertical asymptote is an imaginary boundary line that the graph is going to approach but will not cross. Okay, step 4. We're going to go find the horizontal asymptote. Again, asymptote is that strange word from yesterday, A-S-Y-M-P-T-O-T-E, asymptote. I think it's Latin, which is why it looks so strange to us, or it could be Greek. It's one or the other. Okay, and again, this has to do with the degrees. So we compare the degree of the numerator and the denominator. The degree of the numerator with the degree of the denominator. And we did talk about that yesterday. So I'm going to look back at the original function. For us, they both have an exponent of 1. So they're first degree polynomials in the numerator and the denominator. So in this case, the degrees are equal. So our conclusion is that the degrees are equal. Now, if you remember, there are 3 possibilities. They're either equal, they're the same degree, or the bottom is heavier in terms of it's a larger degree, or the top could be heavier and it could have the larger degree. And we'll handle each one of those cases with an example. So the degrees are equal. If the degrees are equal, then the horizontal asymptote is the line y equal to 0. Yes, that's the x-axis. Okay. And there's our horizontal asymptote. And I'm going to write that down up here in my information. Okay, so that's all the background work. So we found our intercepts and we found our asymptotes. Again, the horizontal asymptote tells me the end behavior. So this is telling me the graph is going to start next to the x-axis and it's going to end next to the x-axis. And that's what this tells me. So all it tells me is just what happens on the ends. A comment about the vertical asymptote. It's nice to think about this in terms of multiplicity. And we'll bring that back in just a second. Okay, any question on the first 4 steps? That's what I call the grunt work. It's the stuff you need to lay the foundation.
So number 4 is on the degree, not the multiplicity, to determine the end behavior?
Correct. So we're going to use the multiplicity over here on the vertical asymptote. And you'll see why in just a minute. So again, multiplicity for us means whether it's going to cross or bounce kind of idea. So, but it's only on the vertical asymptote. It's not going to impact the horizontal one. Any other comments? Okay, and I have to erase it all. Okay. So step 5 is to come in and plot the information. And this is where you see me make some really big graphs. Okay, so we know we have an x-intercept at -2. We know we have a y-intercept at -4. Okay, we have a vertical asymptote at 1. You do need to draw those in. I'm going to put it in color. So I'm going to put a dotted line at x equals -1. And again, that's my boundary line that the graph is going to approach but never cross. Then we also have another asymptote that's at y equal to 0, and it's the horizontal line. It's right on top of that axis. So there are a couple of ways you can do it. If you're using pencil and paper, you can use a highlighter, which works really good. I'm going to try and use the red and put it right on top of my axis, and that's line y equal to 0. Okay, that's all we got. So I have 2 dotted lines. One's vertical, one's horizontal, and 2 points. And from that, I got to graph a function. Okay. So a couple of things to remember as we graph. So plot the information and graph the function. So some guidelines or thoughts to remember is that in each area, you're going to start by an asymptote. And end by an asymptote. So that's what the end behavior in the horizontal asymptote is going to tell us. It's going to tell us where we're starting and stopping. The vertical asymptote is what's going to break this into different pieces and make it look like a bow tie or a volcano kind of function. So you're going to start by an asymptote, you're going to end by an asymptote. Make sure you go through your intercepts. So you need to pass the graph through the intercepts, so include the intercepts, we'll call it. And then I'm going to fit the idea down here of to use multiplicity for the x-intercept and the vertical asymptote, which I call VA just to make it short. Okay, now that's not going to make a lot of sense until we do quite a few of these, but again, that idea of multiplicity is important for us. So those are the only guidelines I can give you. You have to start by an asymptote, you have to end by an asymptote. You need to make sure you go through those intercepts, and when possible, use that idea of multiplicity to help you graph it. Okay, so to graph this, we need to notice that there are two regions. It is still a function. It must pass the vertical line test. So I have to the left of my vertical, and I have everything to the right of the vertical. So I'm going to have a piece over on this side, and I'll have another piece over on that side. Okay, what I'm going to do is use that y-intercept as the easiest piece to work from. Okay, so I have to go through that y-intercept. So in this region, I'm going to start by the vertical asymptote, and to get to this, I'm going to come in like this. And you'll see why once we get it all done. And then I need to head to the next asymptote. Well, over here, I'm going to head off towards the end of my graph, so it's going to approach that other asymptote. So it's going to look like that. So that's what the right side looks like. Now, how do I know it's not crossing over here? Because I don't have an x-intercept listed over here. So it's just going to go towards that asymptote and then keep going by it. Okay, well, what about on the left side? What is this graph doing? Well, it has to start by an asymptote. So over here at the end, it's either going to start above or below. Now, I'm going to do two things. Don't copy them down yet. So if I start above, it has to get to this intercept. And then it could do two things. It could bounce, but wait, we know it's not going to bounce because the multiplicity of the x-intercept on the numerator is a 1. So it has to cross. Well, if it's going to cross, it's going to head on down like that. Why is it not doing that? Well, now I'm going to come back and look at the multiplicity of this vertical asymptote. The multiplicity of this vertical asymptote is a 1. This factor only appears once, which tells me that the graph has got to be bouncing on either side of it. It can't stay on the same side. So it's not doing this because it can't be on the same side of that vertical asymptote. So we're going to go for the opposite side of it. And to force it to be on the opposite side, we're going to start below the red line, cross the x-intercept, and head on up. And now it looks like our bow tie function. Now you can draw it. Okay, so the multiplicity on that vertical asymptote simply tells you whether or not the graph stays on the same side, meaning both bottom or both top, or whether they're on opposite sides. One's headed up and one's headed down. So remember we did those tables yesterday to establish what happens as we get close to it. If you did the same kind of table today, you would see it. And it takes practice. It takes a lot of practice to get these down, but with practice, they're pretty straightforward. So, okay, any comment or question? How can I help understand it? It's a pretty picture. We're good? Okay, I'm moving on then. Let's go do another one. So now we want to graph R of x. And again, we use R of x because R stands for rational. You can call it anything you want. 3x minus 6 all over x squared minus 2x minus 8. So 3x minus 6 all over x squared minus 2x minus 8. let's walk through our steps. So the first thing we're gonna do is the x-intercept. That's the numerator, so that's 3x minus 6 equals 0. And we'll get x equals 2. So that's gonna give you the point 2, comma, 0. What was the next step? Step 2 was to find
Y.
y-intercept. So you're going to come in and let all those x's be zeros. If every single x is a 0, you're going to end up with negative 6 over negative 8, which is what, 3/4. So the y-intercept is 0, comma, 3/4. Okay, next step. The vertical asymptote, the VA for vertical asymptote. That comes from the denominator. So we're going to set x squared minus 2x minus 8 equal to 0. And again, the vertical asymptote is really telling you the domain of the function. So it's the same kind of question. It's just a matter of how we're writing the answer. These are all going to be factorable. So this one factors into x minus 4 and x plus 2. So x equals 4 and x equals negative 2. So again, these are going to be vertical dotted lines when we're all done. Okay, step 4 is the hard one for us because it kind of comes out of thin air. The horizontal asymptote, we're going to compare the degrees. So we're comparing the degree of the top with the degree of the bottom. And again, the only reason I'm using the word top and bottom is that they are shorter to write than numerator and denominator. That is the only reason. What can you notice about the degrees? Well, what's the degree in the numerator?
1.
What's the degree in the denominator?
2.
2. So the top is less than the bottom. So this is what I refer to as bottom heavy. So, oh, Chrome, we did the last one wrong, and that was my fault, not your fault. That was me not paying attention. Let's finish this one, then we'll backtrack. Okay, sorry about that. So it's bottom heavy. And that's when it's y equal to 0. So in other words, the bottom pulls it to that axis. So that's where I messed up on the last one. I didn't yesterday. Yesterday's notes are right. Okay, let's graph what we got and see where we're at. Okay, we have an x-intercept at 2. And you can have more than one x-intercept. Right now we just have single one because the numerator has a degree of 1. The y-intercept is at 3/4. So 3/4. Okay, the vertical asymptote, this time we have 2 of them. One's at a positive 4, so 3, 4. And the other one's over there at negative 2. So I've got 2 of them. So that's going to divide my graph into 3 regions or 3 pieces. So I'll have a left piece, I'll have a middle piece, and I'll have a right piece. Okay, and then we're going to draw that horizontal asymptote right on top of the axis again. And this points out something really, really important. This is why the horizontal is not a true asymptote. A true asymptote you cannot cross. These 2 are true asymptotes. If you cross either x equal negative 2 or x equals 4, you'll be dividing by 0 in the original function, which we can't do. You can cross this horizontal because it only tells me what's going on the left side and the right side. It only tells me what happens at the ends. So notice that this x-intercept is crossing that horizontal dotted line, and that is okay. Because again, the horizontal just tells you the ends. Okay, well now I got to draw the graph. So we're going to pull all the information and try and draw it. I'm going to go for the middle because that's the only place I have numbers at. So because the multiplicity of the x-intercept is a 1, I know the graph is crossing it. Because it has to go through this or y-intercept, I know the graph is doing this kind of behavior. So because it's not bouncing, it's going to head towards that blue dotted line and head on down. On the right side, it is not coming back down because I don't have another x-intercept. So it's going to get pulled towards the blue asymptote at x equal negative 2 and head up. So in the middle, it looks like a cubic function. It's an S shape. Okay, can't bounce anywhere because we don't have more intercepts on this side and we don't have a bounce on this side. The minute I know that, I now know what it's doing on the two ends. Because the multiplicity of the vertical asymptotes are ones, I know that it has to be on opposite sides of those two. It's going to do the bow tie shape. So over here on the right side, it's got to be doing this. Over here on the left side, it's got to be doing this. And there it is. It's a beautiful graph. My kids used to call these bridge functions for some reason. They thought they looked like bridges. If you do graph these on your graphing calculator, you're going to get some really strange answers because what the calculator tries to do is connect this point to this point. So it puts in a line there and it looks like a heartbeat or something. So be careful. Okay, any problem with that? Any comments or questions about how I did it? Notice I went for what I knew had to happen because of the points that were given. And then from there, you can use the idea of the bow tie function to get those other regions. Okie dokie, we're good? Okay, I'm sorry, I do want to backtrack to the last one. Ugh. Step 4 is where we made our mistake. No, I'm sorry, step 4 is where I made the mistake. Not paying attention. And let's see, you guys help me out. We had, this was the first example, just go back in your notes. You had 2x plus 4 over x minus 1. We said the x-intercept was at -2. We said the y-intercept was at -4. We said the vertical asymptote was at 1. That was all great. So it was step 4 with the horizontal asymptote. The degree of the top is equal to the degree of the bottom. That's true also. Where I messed up is when that's true, when the degrees are equal, it's the ratio of the leading coefficients. So we just put it in the wrong space. It's not going to change the overall picture too much, but it does move that asymptote. So again, whenever they're equal, it's the ratio of the leading coefficients. So our horizontal asymptote is going to be y equals, the leading coefficient in the numerator is a 2, the leading coefficient in the denominator is a 1. So again, I'm talking about the 1 that's on the x and the 2 that's on the 2x. So that's going to give me a horizontal asymptote at 2. So where we drew it before, it just has to get moved up. So I apologize. I don't usually make that kind of mistake. Okay, so -2, -4. The +1 is still good for the blue. And again, all we're going to do is then take this one and move it up 2. So y equal 2. Okay. So now it's actually a cleaner graph. We don't have that issue of crossing that asymptote quite yet. So if we're going to go through these 2 points, and we need to start by the horizontal asymptote, we're going to start right below it. We're going to cross those 2 and head on down. It is going to move that second region because the vertical asymptote has a multiplicity of 1. We know that the piece has to be on the opposite side of it to give us that bow tie look. And it's going to be over there. So similar, it just moved that asymptote up to 2. Sorry. Okay, any comments or questions? Hopefully you went back and corrected your notes. I don't think I've ever made that mistake before. That's really embarrassing on my end. Okay, so we've handled the degrees were equal. We did one where the bottom was a larger degree, so it's bottom heavy. Let's go take a look at one that's got top heavy issues. In other words, the degree in the numerator is bigger. So. Okay, so this would be example 3. We do f of x is equal to x squared plus x minus 6 all over x minus 1. So x squared plus x minus 6 over x minus 1. And we'll faithfully go through our 4 steps again. So step 1 is that x-intercept. What do we do to find the x-intercept?
Numerator equal to 0.
So x squared plus x minus 6 equals 0. Somebody factor that for me. What does that factor into?
-3, -2.
Both negative or one positive?
+3, -2.
There you go. So then that's going to give me a -3 and a +2. So my intercepts are at -3, 0, and 2, 0. And again, they're intercepts, write them as points. Okay, number 2, the y-intercept, if you let all those x's be zeros, what are you going to get as your y-intercept?
6.
Yep. You'd get a -6 over a -1, which is a +6. Beautiful. Step 3 is that vertical asymptote. Where does that come from? From the denominator? It's the domain. So we know that x cannot equal a +1, so the vertical asymptote is going to be at 1. Again, that comes from the denominator. Step 4 is the horizontal asymptote. This time, the degree at the top and the degree at the bottom. Okay, so what's the degree of the numerator?
2.
And the degree of the denominator?
1.
Yep. So we can see that it is top heavy. Okay, what that's going to do is it's going to take something that's horizontal and it's going to tip it like a seesaw gets tipped. So this gives us an oblique. Another word is slanted asymptote. So the asymptote is not horizontal. It becomes oblique or slanted. So instead of having a nice horizontal line at y = 2 or y = 0, we're going to have a tipped line. So we have to go find it. And what we're going to do is divide the polynomials. So to find the oblique asymptote, we need to come in and do a division of the polynomials. And luckily for us, we can use synthetic division. And I can use synthetic division because what we're dividing by is a linear factor. So because they have a difference of 1, and this is just x - 1, we can just use synthetic division. And that's true for the homework, and that would be true for a quiz or an exam if you had it on it. We keep it pretty straightforward in the 120 class. So the 1 that we're dividing by is going to go over here. My coefficients are 1, 1, -6. Okay. So we'll go through our synthetic division, which we haven't done for a couple of days, so it's kind of nice. Bring down the 1. 1 times 1 is 1. Adding is 2. Multiplying is 2. Adding is -4. Which is fine. I don't care about the remainder here. So if we were to write this as a polynomial, we start off with an x squared. We now have an x as the depressed equation. So we now have y = x + 2, and that's the oblique asymptote. So again, the 2 is coming from here, the 1 is coming from here. I'm writing it as a line because it's a line that's been tipped. So this is meaningless. And the reason it's meaningless is, again, the oblique asymptote is telling me where the graph starts and where the graph stops. So it's telling me the end behavior. And if I'm out there at infinity, does -4 impact infinity? No. So whether or not I add or subtract 4 to it is not going to make a big difference. So we're going to ignore that. Okay. And I think we have everything we need now. I'm going to erase it. You guys are going to have to help me remember what everything is. So -3, 0, 2, 0, 0, 6, x = 1, and y = x + 2. Okay, that's all my information. Those of you headed to pre-calc, you'll pick up long division in pre-calc. So if you need it, they will teach it to you there. Okay, what do we got? So we've got -3 and +2. I've also got a positive 6. I have a vertical line at positive 1. So there's my vertical line at positive 1. And again, its multiplicity is 1, so I'm expecting it to do opposite sides, opposite quadrants kind of thing. So, okay, now we're going to go graph in this line. Well, it's just a line. It's y equal x plus 2. It's got a y-intercept at 2, and it goes up 1 and over 1, up 1 and over 1, up 1 and over 1. So now I can draw in my dotted line. So that should be over here. So trying to get it in the right spot. So again, what's happened is our nice horizontal line that we had in the previous 2 examples has gotten tipped, and we end up with something that looks like this. So y equals x plus 2. It is still a dotted line. It's still an asymptote. Now that we have that in, we can come in and draw the graph. Again, remember, it's going to start by an asymptote. It's going to end by an asymptote. So on the left side, the only asymptote that's out there is the dotted red line. So we're going to come in and start right above it, because I'm going to cross here and I'm going to cross here. It's going to come in and do a nice gentle arc between those intercepts. So it looks something like that. Kind of hard to draw without graph paper and a grid that's consistent on your scales. So it looks something like that. It hits that nice blue line and it heads straight up. Again, it won't hit it, but it's close to it. Okay, on the other side, we have one dot. We're going to start by the blue line. We're going to start below, because all the multiplicities are odd. We know everything's in opposite regions. So it's going to look like this. And it's going to head towards that y equal x plus 2 line. And that is an oblique or slanted asymptote. Comments or questions? Okay, what you will notice that as we go through these, that they're getting a little quicker to do. So the beginning one took some time, but they're getting a little bit faster. Okay, let's go do one that has a multiplicity issue, just so you've got one in your notes. So let's do g of x is equal to x plus 2 over x minus 1 squared. So x plus 2 over the quantity x minus 1 squared. And we walk through the steps again. So you tell me, what's my x-intercept?
-2.
Good job. Somebody else tell me, what's my y-intercept? So if all those x's are zeros, what's y going to be?
2.
Yep. Good job. Okay. The vertical asymptote is coming from the denominator again. It would be x equal to 1. I'm going to make a note to myself that it's got a multiplicity of 2. That's that outside exponent impacting the world. Okay. You don't really need that, but it's just a note to myself. Okay, what about the horizontal asymptotes? Are the degrees equal? Is it top heavy or is it bottom heavy? So where's the larger degree?
Bottom heavy, correct?
Yep. So the degree of the top is a 1. The degree of the denominator is a 2. So it is bottom heavy, which pulls it to the x-axis. So it's the line y equal to 0. So, okay. It's all of our information. Let's go graph it. So -2 for x, +2 for y. We have a blue dotted line at +1. And we have a horizontal asymptote on top of the axis again. That's what we got. Okay, well, the only place where we have points is on the left side. So let's go tackle the left side first. Okay, because the multiplicity of the x-intercept is a 1, we know it has to cross here. So my guess what it's doing is it's starting right below. It's going to cross and hit the y-intercept, and then the blue asymptote is going to force it up. So it looks something like that. And that's good enough for us. For those of you that head into a calc sequence, what you're going to probably see is that it actually comes in and does some kind of dip and does this. But we need calculus to see that. So for us, we don't care. We don't have any tool to find it other than using a calculator, which we don't like to do. So, yeah, but now what about on the right-hand side? So normally I would say, well, it's opposite. It's going to be down here. However, because the x-intercept actually, I'm sorry, because the vertical asymptote has got a multiplicity of 2, the graph is not going to be on the opposite side. It's going to stay on the same side. So it's going to look something like that. So it's going to be a volcano function because of the multiplicity of the vertical asymptote. So, and there it is. So it looks a lot different the minute I added that square in. If you added a square in the numerator, you'd have a bounce at the x-intercept, which we know how to deal with. So, comments or questions? That's a volcano function. Okay, we got one more to do, and then we're going to call it good. So this is a graph with a hole. So r of x equals x squared plus 4x minus 5 all over x squared plus x minus 2. So x squared plus 4x minus 5, x squared plus x minus 2. Okay, so what we're going to do, the first thing we're going to do is actually come in and factor the numerator and the denominator just to make it easier to pull information out of. So when I factor the numerator, it's going to factor into x plus 5 and x minus 1. The denominator is going to factor into x plus 2 and x minus 1. And so for the first time in our course even, we noticed that we have the same factor in the numerator and denominator. Well, it's a fraction. We can just cancel it. So what we're really graphing, oops, I don't even need parentheses, is x plus 5 over x plus 2. So we factored out that factor. We canceled it. Okay, now let's walk through our steps. Okay, somebody tell me my x-intercept.
-5.
Somebody else tell me my y-intercept.
(5/2).
Yeah, which is weird, but it's okay. Okay, where's the vertical asymptote?
-2.
Fantastic. Okay, and now we're going to come in and talk about the horizontal asymptote. Let's make sure we've got it correct. The degree in the numerator is equal to the degree in the denominator. They're both first powers, right? So then it's y equal the ratio of the coefficients. And the coefficients are the 1 that's on each of those x's. So it's y equal to 1. So when the degrees are equal, it's the ratio of the coefficients. Okay, there's all our information. And again, we didn't even really need to write out anything other than the information. There was no work involved. That should make you guys happy. X-intercept at -5. Y-intercept at 5/2. 5/2 is 2.5. So vertical asymptote is at -2. And the horizontal asymptote is at y equal to 1. Okay. You should be to the point where you can start drawing some stuff in on this, right? So on the left side, over on the left side of the blue line, it's got to go through that x-intercept. And again, its multiplicity is 1, so we know it's crossing. So it's going to start right below the red line and head down towards the blue line. So starts by the horizontal, ends by the vertical. On the other side, because the multiplicity is odd for the vertical asymptote, we know it's got to be in the opposite section, which means up. So we're going to start by the blue above. We're going to cross the y-intercept and head off towards the red. Now, at some point, it may cross that red one, right? But we don't need it. It doesn't add to my picture at all. So I'm just going to leave it the way it is. So far, so good. The problem is the original function had this x minus 1 as a factor that we canceled out. That creates a hole. So because we canceled, because we canceled, x minus 1, we have a hole at x equal 1. And that x equal to 1 is coming from setting that x minus 1 to 0. So in other words, if I asked you the domain of the original function, you would tell me that x can't be a -2 and x can't be a 1. So I have to account for that other 1 from the domain issue. So literally all I'm going to do is I'm going to come over to my picture. I'm going to come into a value of x equal to 1, and I'm going to go up to my picture, and then I'm going to put in a hole. So I literally am going to erase and make a hole. And it's simply because we canceled, we have to account for that in our domain. So in other words, you cannot plug 1 into the original function. Even though it factors out and you got rid of it, you still can't plug 1 into the original. So you create a hole. You'll have one of these. It's like the end problem, I think. No, second to last problem. So, okay. Any comments about graphing those rational functions?
No, I think I'm good.
Yeah, they should be kind of fun once you get the steps down. It's a matter of getting those steps memorized. So, okay, so tomorrow we're going to do section 5.4, and then on Thursday we'll talk about the R3 review and go over some problems that are similar or part of that review for you guys. So, and don't forget you got a discussion you should be working on too. So, have a great day. Enjoy it.
You too.
You
Have a good
too.
one.
Bye-bye.